Hi everyone, my name is Anya and today on Math and Science Concepts, I'm talking about stoichiometry. And I'm going to make it simple and easy for you to understand. But before we begin, make sure to like, share, and subscribe and hit that notifications bell so that you never miss another one of my informative videos. So let's get straight to it. In Greek, stoichion means element and metron means measure. So stoichiometry literally translates to the measure of the elements. Pretty cool, right? It gets even cooler. What is stoichiometry? Stoichiometry is like the recipe for a cake, but instead of baking, we're dealing with chemical reactions. At its core, stoichiometry is the study of the quantitative relationships between the reactants and the products in a chemical reaction. When chemists conduct experiments, they need to know how much of each reactant to use and what amount of product to expect. For example, using the cake analogy, let's say you used 2 eggs, and for every egg, you get 3 pounds of cake. Then if you use 2 eggs, then you'd get 6 pounds of cake. That's using a stoichiometric ratio. When chemists conduct experiments, they use these stoichiometric ratios to figure out how much of each reactant will mean how much of each product. Stoichiometry provides these answers, ensuring that chemical reactions are efficient and effective. Before applying stoichiometric ratios to chemical equations, you'll need to know molar mass. Molar mass is a useful chemical ratio between mass and moles. The atomic mass of each individual element as listed in the periodic table established this relationship for atoms or ions. For the compounds or molecules, you'll have to take the sum of the molar masses times the number of each atom in order to determine the molar mass of the compound or molecule. To grasp stoichiometry, you first also need to be familiar with a few key concepts. First of all, moles. Just like a dozen represents 12 items, a mole is a specific number of molecules, approximately 6.022 times 10 to the 23rd molecules, also known as Avogadro's number. See my chemistry videos playlist for more on Avogadro's number. Secondly, molar mass. This is the weight of 1 mole of a substance, typically expressed in grams per mole. It tells you how much 1 mole of a substance weighs in grams. And finally, mole ratios. These ratios come from the coefficients of valence of chemical equations or reactions. They tell you the proportion of reactants and products in a reaction. These are also called stoichiometric ratios. So now let's go on to figure out some real-world applications for stoichiometry. Stoichiometry isn't just a topic in your chemistry textbook. It has real-world applications. Pharmacists use stoichiometry to mix medications, environmental scientists use it to track pollutant levels, and engineers apply it to design reactors. Understanding stoichiometry means that you're learning a skill that scientists use and professionals use daily to make the world work as it is. So our first example of real-world applications is cooking and baking. Recipes are essentially stoichiometric guides. They specify the precise amounts of ingredients, reactants, needed to produce a specific amount of the final dish, the product. For example, a cake recipe provides ratios of flour, sugar, eggs, and other components. Adjusting a recipe to make a larger or smaller batch involves applying stoichiometric principles to maintain the correct proportions and ensure the desired outcome in terms of taste and texture remains the same. Too much or too little of an ingredient, like baking soda, can significantly alter the result, according to Brainly.com. Our second example is household cleaning products. Many cleaning agents involve chemical reactions where ingredients are carefully balanced to achieve the desired cleaning action without causing harm to the surface. For instance, when mixing bleach, a base, with water, understanding stoichiometry can help avoid overly concentrated or overly diluted solutions that could damage surfaces or not be effective at all. Our third example is gardening and fertilizers. Fertilizers require specific ratios of nutrients to promote healthy plant growth. Stoichiometry guides the formulation of fertilizers to ensure plants receive the necessary elements in the correct proportions, preventing over-fertilization, which can harm plants, or under-fertilization, leading to nutrient deficiencies and deprivation. Our next example is product formulation. Now, this is a general use, but whether it's shampoos, perfumes, or soaps, manufacturers use stoichiometric calculations to determine the exact amounts of each ingredient needed to create the products with the desired properties and quantities. Our next example is pollution control. Stoichiometry helps environmental scientists analyze and reduce pollutant levels. For instance, calculating the efficiency of a pollution control device in a car or industrial setting relies on stoichiometric principles. Another usage is in the pharmaceutical industry. In drug development and manufacturing, stoichiometry is vital for determining the correct proportions of reactants to produce specific drugs, the products, efficiently and safely. It also helps in quality control by assessing the purity of substances and ensuring the correct dosage. And our last example is energy production. Stoichiometry plays a role in optimizing the efficiency of chemical reactions involved in energy generation. For example, controlling the ratio of fuel to oxygen in combustion reactions for power plants is crucial for maximizing energy output and reducing emissions. And now we come to the types of reactions. There are 7 basic types of reactions. Number 1, combustion. Combustion is the formation of CO2 and H2O from the reaction of a chemical or multiple chemicals and O2, oxygen gas. Our next type of reaction is combination or synthesis. Combination is the addition of 2 or more simple reactants to form a more complex product. 3. Decomposition. Decomposition is when complex reactants are broken down into simpler products, pretty much in the name. Number 4, single displacement. Single displacement is when an element from one reactant switches with an element of the other to form 2 new reactants. It's kind of like a dance. Like, let's say you're at the party and there's a couple, and then there's one person standing to the side. The person standing to the side will steal the place of one of the people in the couple and kick the other person out. That's single displacement or replacement. Now, 5, double displacement. Double displacement is when 2 elements from one reactant switched with 2 elements of the other to form two new reactants. It's again like a dance. But now there's nobody alone. There's two couples, and the two couples switch their partners to make two new couples. Our sixth type of reaction is acid-base. Acid-base reactions are when two reactants form salts and water. So now, our last one, precipitation. Precipitation reactions are when multiple aqueous or liquid reactants react to form at least one solid product. There can be multiple solid products, but the minimum is one. And now moving on to balance. Balancing chemical equations in stoichiometry involves adjusting coefficients in front of chemical formulas to ensure an equal number of each type of atom on both the reactant and product sides of the equation, thus obeying the law of conservation of mass. This process ensures that the equation accurately represents the quantitative relationships between reactants and products in a chemical reaction. So the steps to writing a balanced equation are, first of all, write the unbalanced equation or the base equation. That is, write the chemical formulas for all the reactants and products without considering the number for each. Secondly, identify the elements that are not balanced. Look for elements with unequal numbers of atoms on both sides of the equation. This might require some calculation, but not necessarily. Thirdly, balance the atoms one at a time. Start with an element that appears only in one reactant and one product. Adjust coefficients, numbers in front of the formulas, to balance the element. And continue balancing these elements. Move on to the next element, repeating the process, adjusting coefficients until all the elements are balanced. And now, just for a final check, verify the balance. Count the number of atoms of each element on both sides, the right side and the left side, the product and reactant side of the equation, to confirm that it is actually balanced and everything is equal. And finally, to make it truly complete, indicate the states of matter. Add the S, the L, or the G, or the AQ. S means solid, L means liquid, G means gas, and AQ means aqueous. And this is to indicate the physical state of each substance in the reaction. And now moving on, we'll balance an example now. Let's balance the following unbalanced equation for the reaction of hydrogen and oxygen to form water. H2 plus O2 becomes H2O. Write the unbalanced form of the equation. H2 plus O2 is H2O. And now we're going to follow the steps. Write and balance the chemical reaction. Start with the given mass, moles, or volume, convert to moles, and then moland. Convert to moles of another compound or atom. And now we have to convert to the final unit. So we've written the unbalanced form. Now we identify the unbalanced elements. Oxygen is unbalanced because 2 on the left, but there's only 1 on the right. So let's balance the oxygens. We'll add a coefficient of 2 in front of the H2O. That makes it H2 plus O2 is becoming 2H2O. And now we balance the hydrogen. Now hydrogen is unbalanced. There's 2 on the left, but there's 4 on the right. So we add a coefficient of 2 in front of H2, making it 2H2O plus O2 becomes 2H2O. And now we verify the balanced equation. 2H2 as a gas plus O2 as a gas becomes 2H2O as a liquid. Some key points to keep in mind when balancing these equations are the subscripts. Don't change the subscripts within the chemical formulas, as this changes the identity of the substance. No, we don't want to do that. Coefficients. Only change the coefficients in front of the formulas to balance the equation. As I said before, do not change the subscripts. And our balancing strategy. Start with the elements that appear in the fewest formulas and save the most common elements for last. Mole ratios. Once balanced, the coefficients in the equation represent the mole ratios of reactants and products, which are essential for stoichiometric calculations. And finally, stoichiometry. The balanced equation allows us to predict the amount of reactants and products involved in a chemical reaction using the mole ratios or stoichiometric ratios. And now we'll look at another example here. We have to balance SnO2 plus H2 turns into Sn plus 2H2O. So let's focus on balancing hydrogen. The reactant side has 2 oxygen atoms, while the product side has 1. So this will be the first one that we'll have to balance. But first, let's identify the atoms and their counts. The reactant side, SnO2 plus H2, there's 1 tin, 2 oxygens, and 2 hydrogens. And now the product side, Sn plus H2O, has 1 tin atom, 1 oxygen atom, and 2 hydrogen atoms. So oxygen is the only one that's unbalanced right now. So as I said before, we'll focus on balancing oxygen. So we'll say SnO2 plus H2O becomes Sn plus 2H2O. Now we've balanced the oxygen so far. And now we have to reevaluate the atom count. On the reactant side, SnO2 and H2O, there is 1 Sn, 1 tin, 2 oxygens, and 2 hydrogens. And on the product side, Sn plus 2H2O, there is 1 tin, 2 oxygens, and 4 hydrogens. So now, let's balance the hydrogens. Moving on to the next slide where we'll continue. We'll balance the hydrogens. First of all, we'll say SnO2 plus 2H2O turns into Sn plus 2H2O. And now we'll do our final check, count the atoms on both sides again, and we figure out everything's all balanced. So now, since the number of atoms of each element is now the same on both sides, the equation is balanced. Now we have to indicate the physical states of the reactants and products, i.e. the liquid, gas, solid, aqueous, all of these states. To do this, you'll need to be familiar with the properties of various compounds, or you'll need to be told what the phases are for the chemicals in the reaction. Oxides are solids, hydrogen forms a diatomic gas, and tin is a solid. And the term water vapor indicates that the water is in the gas phase. So we'll find out that this chemical equation will turn out to be SnO2 as a solid plus 2H2 as a gas turns into tin as a solid, Sn, plus 2H2O as a gas. And now, finally, a fun fact. To end this presentation on stoichiometry, here's a fun fact. When cooking, if you run out of one ingredient, stoichiometry can help you calculate how much of the other ingredients you'll need to maintain the same proportions. Say for cooking, a recipe is used to make a dish, let's say brownies. 1/2 a cup of butter, 2 ounces of chocolate, 1 cup of sugar, 2 eggs, 1 teaspoon of vanilla, 2/3 a cup of flour, 1/2 teaspoon baking powder, and 1/4 teaspoon salt for 24 brownies. What if I want 36 brownies? The ingredients don't change, but the amounts do proportionally. 1/2 cup of butter, 2 ounces of chocolate, 1 cup of sugar, 2 eggs, 1 teaspoon of vanilla, 2/3 of cup of flour, 1/2 teaspoon of baking powder, 1/4 a teaspoon of salt for 24 brownies becomes 3/4 cup of butter, 3 ounces of chocolate, 1.5 cups of sugar, 3 eggs, 1.5 teaspoons of vanilla, 1 cup of flour, 3/4 teaspoon of baking powder, 3/8 teaspoon of salt for 36 brownies because we multiply everything by 1.5. And that's the end of this presentation. Please remember to share and subscribe, and see you next time. Ciao!